Why?
Here to introduce our second speaker, Michele. He will tell us about 5D conformal method.
Okay. So thank you very much. Let me write on the board things that the organizers want to see. Thanks for having me, Giuliano Alessandro. This is and Giulio. And it's always a pleasure to be back at CISA, and I mean, I was a student here, and it's a pleasure to be back at my alma mater from time to time. I followed many lectures in this room, in fact, a long time ago. This is a project that I'm finishing in these days together with Mario De Marco, Michele Graffeo, and Andrea San Giovanni. And this is a project that will appear on the board soon. And two of them, Mario and Andrea, were students of Roberto, who's in the audience. And he was a student of Hugo, and these are also it's also it's a CISA based somehow like and University of Trieste, because Andrea is from UNITS. They were in Uppsala with some fellowship from Italy. Andrea got the Lincei, and Mario was supported with the Della Riccia. And while they were here in Uppsala with me, we started looking into geometry and the interplay with conformal field theories, and it came out into a nice story that I want to tell you today. So we know, like, that from string M and F theory, one of the outcomes is that there are higher dimensional superconformal field theories. No? So for a long time, these systems were believed not to exist, but thanks to geometric engineering tricks, we know that now they do. Of course, because of representation theory, there is this famous theorem by Nam, the superconformal algebras exist only in space-times of dimension less than or equal than 6. And why do we care about these theories? Well, we care about them because they are very interesting, exotic objects, but also because there are these possibility of studying dimensional reductions. So like we can denote them like this. This is a notation that I introduced with Cyril a while ago. And so we start from a CFT in D dimensions, and we end up with a CFT in D minus K dimensions, where MK is a valid, say, BPS background, if you wish. So here I'm hiding a lot of background fields and choices of R symmetry in the notation, but these are literally compactifications, valid compactification preserving supersymmetry of these 6-dimensional theories. I'm using this notation because if you just do the dimensional reduction, you would get a DM, this thing. And you will keep a lot of K of modes, the higher harmonics, if you wish, of your fields. But it's always possible to project down to the bottom of the KK tower, to the lowest Landau level for this background. And if you start from a theory that is conformal, you expect to end up with a theory that is conformal as well. No? And so there is some sort of a dimensional reduction functor, if you wish, from the category of conformal field theories in D dimension to the one in D minus K dimensions. No? And the reason why these things are interesting is that we learn from these geometries, from this structure, we learn many non-trivial features of theories in lower dimensions follow just from the existence of the higher dimensional ones. No? So like applications, we have seen application to dualities, to non-invertible symmetries. There are correspondences, like AGT and so on, and more, no? Like this stuff that people in the audience are more or less probably all familiar with in one way or another. So I won't spend much time reviewing this. These are just applications. There are motivations to study these things, to study higher dimensional CFTs, and to try to understand whether there are some structures that govern them, no? Study them, like classify them, understand them. So they are rigid. extremely constrained. In fact, of all superconformal algebras that NAM constructed for d equal to 6, there are only two, OSP 8,4 and OSP 8,2. These are the two superconformal algebras in d equal to 6 with a good stress energy tensor. So there are only two. This one is realized in the 6D 2,0 theories, and this one is the one for 6D 1,0 theory. No? And so, like, they're very rigid, extremely constrained. It might make sense to try to devise classification schemes for these objects. No? And why one does look for classification? Well, one wants to understand what are generic properties in this family of theories, and also wants to find exotics. No, this is like the reason why one classifies things. No, like either understanding generic patterns or finding exotics. No, like discover exotics. So, what are classification schemes that have been devised for these gadgets, for these theories? So, mostly geometric. No, geometric. In this case, geometric engineering. So from the 90s, it's known that if you take type 2b on a C2, on an orbifold singularity where gamma is a discrete subgroup of SU2, a finite subgroup of SU2, there is an ADE classification due to Mackay correspondence, no? And you get an ADE series, no, of these 6D2,0 theories from type 2b on this orbifold. No? These are the 6D2,0 CFTs, and they are representations of this algebra, no, in fields. There are ways of reproducing this classification using field theory now, like one is due to Henningson from BPS strings, and one is due to Cordova, Dumitrescu and Triligator, and is based on field theory, with the axiom that the ds1 of xg is n equal to 2 Superior-Mills of type G. There is can you see if I write here? And can you read my handwriting? Two separate questions. The answer is no to both. Yes. Okay, so I will try to do better in both cases. So this blackboard is off limits. Can you? It's still okay, but I should write capital letters probably. That's the compromise. Okay. So I was saying, no, here you have a BPS string approach by Mans-Henningson, which reproduces this ADE classification from studying the properties of the Dirac pairing between BPS strings. And then there is this approach, field theoretical, which is based on the fact that you assume as an axiom that the reduction on a circle of this theory is n equal to 2 Superior-Mills of type G. And if you add this axiom field theoretically to the construction of 2,0 CFTs, you find out that there is an anomaly that can be matched across this circle reduction only if G is simply laced. Simple and simply laced, and so you are restricted to ADE. There are examples of n equal to 2 Superior-Mills theory with non-simply laced gauge groups, but they don't correspond to 6-dimensional 2,0 CFTs with non-simply laced algebras. They are obtained from this one with some twisted reductions, and there is a nice argument field theoretically that reproduces this classification from this side. On the 6D 1,0 side, the story is very similar. There is also a geometric version. Sorry. No, open, but it's among the features that people believe these theories have, because you start from type 2b on this geometry, you put it on a circle, you can T-dualize, you go to type 2a, and you get a gauge theory of this type. No? So based on that, you expect that this is kind of sound, but I agree. Like, field theoretically, nobody ordered that. Here also geometric approach, no? An analog of type 2b in this case is F theory, and the analog of gamma is you get the orbifolds of C2 with U2 is a subgroup of U2 now, not SU2, because you are in F theory, so you are allowed to use a Keller base, not a Calabi-Yau. But on top of that, there is extra data, no, a non-Kodaira fiber. Kodaira fibers occur in codimension 1. These singularities would be in codimension 2, and so you decorate them with fibers that are more singular than the Kodaira ones. No? And then you blow up, you resolve, you understand what is the structure, but this is more or less the geometric classification scheme. And now, for 6D1,0, however, there is also another classification scheme, which is called the atomic classification. No, atomic classification. Very dangerous, yes, very dangerous. Very dangerous to play with these atomic things. But the idea is, behind the 6D atomic classification, is that these 6D CFTs, and this is an idea that borns, like you start from geometry, you look at these geometries for a while, and you recognize that there are patterns, no? And the patterns is that the 6D CFTs are like molecules built out of elementary constituents. No, so there are structures in which you choose certain nodes labeled by a gauge algebra. They play the role of a gauge symmetry, and there are links between these nodes. And these links, if G is say SUK, they are just bifundamental matter, something like this in the bifundamental of SUK. But if G is any like SO2K or say E6, E7 or E8, then there is not a bifundamental of E8. So what do you get? You get from the structure that you find 6D superconformal theories that generalize bifundamentals. They have a flavor symmetry which is E6 times E6. You can gauge it and you can form quivers of those. Okay. So these are the so-called 6D conformal matter theories. And there are, in 6D, it turns out you can do everything with things that are like fundamentals and things that are like bifundamentals. Yeah. It's not a gauging, no, indeed. It's an operation which is called fission. Well, gauging is fusion, and ungauging is fission. No? Nomenclature inspired by the structure of atoms. No? But the idea is, you see, in 6D1,0, there is gauge anomalies. No? These gauge anomalies are typically cancelled exploiting Green-Schwarz mechanisms. So you want to gauge a symmetry, you don't just supplement it with a vector, you have to supplement it with a whole structure, which involves also an anti-self-dual or a self-dual tensor multiplet that can cure the anomaly via Green-Schwarz mechanism. Geometry knows that. If you study F theory, whenever you do this gauging or ungauging, you are taking a divisor and you're making it compact, and you are dressing it with a Kodaira fiber of type G, and when you do that, this will provide you with the gauge degrees of freedom. This one will, with the D3 brace wrapping on this one, will provide you with BPA strings, and the decomposition of the C4 field on the primitive forms in this base will give you the self-dual tensors that you need for the Green-Schwarz mechanism. No? So this is an operation which is called fusion. It's the proper generalization of gauging in 6 dimensions. No? If you want to do a gauging in 6 dimensions, you don't just couple a current to a vector. You need to do more. Like it's a more complicated operation. And indeed, like you have to, like in field theoretical terms, the idea is that you have vector tensor systems, no? And you use those to gauge these generalized symmetries of 6D theories.
But what do you gauge? A subgroup, the whole group?
No, the whole group. No, the whole, like E6, say. You want to, each node, no?
With the global symmetry G, and then you,
no, the idea is that a node is a gauge group G, no? Gauge group, together with the tensors that you need needed for the anomaly. Yes, exactly. No, like no.
the arrow, you are gauging it.
I would more say that, like, what I want to say is that the structure of this theory is like a quiver of linear type, more or less like this, no? Where the nodes of the quiver are labeled by gauge symmetries, and the edges are labeled by fundamental matter theories, no? If the gauge groups are SU type, the bifundamentals are actual bifundamental fields, it's fine. If not, then, like, geometry says that there is more degrees of freedom there. Like, for instance, for E6, you study the collision of two E6 singularities in the F-theory base. You find that they smash on a non-codaira. You resolve it, and you find that these E6 singularities now give rise to a smooth geometry, well, with resolutions, or a resolution pattern like this, where here you have also an enhancement to a codaira fiber of type SU3. No? So this is codaira E6, codaira E6. No? And like this would be the 6D E6 E6 conformal matter. No? It has more degrees of freedom. There is a lot of, it has a tensor branch. No? It's like a theory with a proper Coulomb branch or a tensor branch that once shrunk behaves like a bifundamental. No? And so the spirit of this atomic classification is that instead of classifying the geometries, you can classify the atoms and the ways in which you can glue them consistently. And the gluing is dictated by anomaly cancellation. So there are, like, it's a concrete procedure. It's not random. And there are rules for how to go, and you can classify them. You get these linear quivers. There are some tails. Sometimes you can have some gauge groups that admits trivalent gaugings, but that's more or less it. You can just go through the whole list with fundamentals by fundamentals, these gauging operations, and sometimes some extra data involving, I don't know, for instance, freezing certain singularities. No? You can obtain more general basis from like declaring that there are some non-geometric effects associated to the freezing of certain singularities, which are dictated from F-theory from the presence of O7 plus planes, like in the. But this is just motivation, okay? This is just a story that exists. It was told about 10 years ago, more or less, no? And it's about the classification of these gadgets, no? So one question is, okay, but we know that there are many more CFTs. Can we do atomic classification of those? Yeah.
The 6D conformal matter refers to the theory before you gauge the nodes or after you gauge the nodes?
Before.
Before, so there is no gauge group essentially.
There is, I mean, if you have a complicated, like in this case, there is a gauge group that is SU3, for instance, because it's like it's a complicated, it's a conformal field theory on its own, no?
But it's like an isolated conformal field theory.
All higher dimensional CFTs are isolated, no?
It would have like a moduli space.
It has a moduli space. It has a tensor branch, for instance. So because it behaves like a generalized bifundamental. No, like it's like a building block. No, it's like there is no bifundamental of E6. If you try to build it using fields, you will just get troubles in 4 dimensions with the explosive. Like you will just go and get a theory which has a beta function which is too high. No, if you try to do it in 6 dimensions, you get things that don't make sense from the perspective of anomaly cancellations. But from geometry, you see that there are these things that occur in patterns, so you can form quivers of those. Like there is a quiver that has E6 gauge nodes. It's a linear. You can add as many of them as you want. No, and in between these E6s, there are the same copy of the same building block. No, and that's why we call it matter, because it's like a Lego piece in building these generalized quivers. No, with gauge theories, you build the quivers from prescribing gauge nodes and matter, and here it is the same. No, like. You have gauge nodes and like some form of matter. Yes.
Suppose you have just one node.
Mm-hmm. If you have just one node without the matter, like this.
I guess this
Ah, okay.
Which is this here?
There are some. This is part of the list of atoms. No, like there are.
But corresponds to?
This is a single gauge group, no, with a single tensor, say.
Oh, it's global.
No, this is.
No, it's gauge.
Is gauge. Like the idea is that these links, sorry, maybe it's confusing notation. No, these links have global symmetry G. No, And then you gauge them. You gauge a diagonal subgroup, if you wish. No, this is how you build quivers. No, this is where I was going.
When you write this ungaged block,
Yeah.
this corresponds to some SFT with global symmetry given by the
Yes, exactly. Global symmetry of type G times G. No, like a bifundamental. No.
But also this tensor matrix.
And then it has a tensor branch. It is a CFT on its own. No, it's an interacting. Yeah. Yes, exactly. It is an interacting.
Standard class S theory.
Yes, yes.
Because the single node is already HT.
It's already KCO, but in fact, in class S, and that's you're anticipating the next part of the talk, which was, no? So there is this structure, okay, there are some building blocks, you can glue them together in consistent ways, no? You can call it fusion, fission, whatever name Heckman comes up with, but like it's like a generalization of gauging, no? It's something that we are more or less familiar with. And one can ask, like, is there an atomic classification in other dimensions, no? I don't know. Is there a 4D atomic classification? No? But, like in 4D, we know these theories very well, as Cyril has discussed. No? In 4D, we know these theories very well, but all the classification schemes that I know so far are geometric in nature. No? There are geometric classifications. There is the Argire-Martone scheme, there is the Xie-Yao scheme, there is the schemes devised by Sergio and Matteo, no? Like, there are, various types of classification schemes. One is based on special Kähler geometry, one is based on the hyper-Kähler geometry of the reduction on a circle of the theory. There is this Donaghy-Witten, no? Integrable system associated to the Coulomb branch of these theories. You can try to classify them if they are conformal. They are associated to hyper-Kähler singularities. And there are other schemes based on type 2B engineering, no? Again, yeah, is there a notion, no? Like, it's just a question, no? There are geometric classification schemes, but, is it possible to find an atomic classification for 4D theories? Like, let's look at it. Let's look at class S theories, no? N equal to 2, sorry. I want 4D n equal to 2. Yes, this is good. This is a good point, no? From this perspective, no, from the perspective of the 6D theory, we learned that if the theories have high supersymmetry, high amount of supersymmetry, they behave like noble gases in the Mendeleev table. No, they don't want to form quivers. They don't want to bind together. They are there perfectly beautiful and AD classified. No, n equal to 4 superior Mills. In 4D n equal to 4 is the example, no? Perfect, beautiful, you cannot touch it. I mean, it's beautiful theory, but you cannot do anything more to it. Like, it's already, it's there, it has that amount of supersymmetry, it's there. 4D n equal to 3 theories also are quite rigid objects. They are also based on classifications associated to crystallographic groups now, like complex crystallographic groups are associated to these n equal to 3 theories. N equal to 2 have 8 supercharges. They belong to this, like, you can get them from toroidal reduction of these ones. And so one could expect that, like, they have geometric, but they might also have an atomic classification. They might have atoms, no? And indeed, if you look at class S, it works, no? Like, if you do class S, you do the generations of Riemann surfaces, no? And you find that the building blocks are these fixtures, the spheres with 3 punctures, no? And then all the rest is obtained by gauging, no? There are maybe decorations, discrete data, discrete gauging, some discrete operations that you can do, but essentially, like, you have a finite list of building blocks and then you play with it. There are also, however, but here one could complain, there are Argyres-Douglas theories, no? Or generalizations thereof, no? Do they belong to this atomic, are they special atoms, are they not? I mean, it's more of a philosophical question, because, yeah, in a sense, if you choose a gauge theory with a rank high enough, you can probably tune it in such a way that it reaches an Argyres-Douglas point of the type that you prefer, no? So it's a question of taste, more than, but more or less, it's just yes, Cyril. Yes. Well, they are trinions. They are the class S trinions, not the. That's the question, no? Is it true? No, I think that the trinions are enough. Like, if you if you buy the fact that you can reach any Argyres-Douglas point from a big enough class S geometric engineering by tuning it, colliding singularities, get some irregulars, some I don't know, like some definite field theory operation, then the atoms are the trinions. The trinions contain the fundamentals, contain the bifundamentals, and give rise to more general types of vertices for the quivers. No? In 6D, you get these linear quivers. In 4D, you get quivers that have trivalent vertices in general. No? But more or less, again, you have these topologies that can be used to classify theories, if that's your aim. But
in 4D, I have the theory, and then I can gauge it.
Mm-hmm.
I gauge it, and I can
Yes.
probably it's an only. I mean,
Yes.
In Poland, but let's say every Gaussian coupling is a gauge.
Yes. Yes.
In 6D, you only evaluate the singularities, and then what you mean by atoms is like it's not fully isolated. There's some simpler isolated singularities. And
Yes.
This kind of operation.
Yes.
More like an RG flow.
Yes.
Well, is it an RT flow?
It is.
My question, yeah.
No, it's a fission. Like fission is not really an RG flow, no? Yeah. It's the analog of gauging. It's not. I wouldn't say it's.
Is there a sense in which the reduced to gauging?
It's a reverse RG flow, if you wish. The fission is a reverse RG flow, no? Like it's the analog of you have a theory with a gauge symmetry and you send the gauge coupling to infinity to zero, no? And that's the fusion. It should be thought of in that term. You have a theory that has a gauge symmetry and you can like send the gauge coupling to zero, which is tanking the volume of that curve to infinite size, no? So I think no, the analogy kind of holds, no? And class S description kind of says that it works like that, no? Many complicated theories arise from just spheres with three punctures and gluing, no? And that's a nice feature, no? It's combinatorial, beautiful, summarize a lot of things. So then the question is natural, no? Okay, for t n equal to 2, more or less we can buy it. It can have some sort of anatomic classification. Let's think about 5D. 5D CFTs are even more rigid. There is a unique superconformal algebra in 5D. It's the F4 superconformal algebra. They can be represented exploiting theories that have a geometric engineering in M theory now, or in type 2B using PQ5 brains. And there have been geometric classification schemes. Again, also in this case, no? Geometric. There are some that arise from starting from a 6D theory and do a reduction, say, call it a T, and do a reduction to a KK theory, and looking what happens to the modular space of this one. So these possibilities have been classified. There have been a lot of work in this direction. There are some which start intrinsically from geometry, like again, Xie Yao have a proposal from Gorenstein singularities, no? Calabi-Yau singularities. Building on previous work by Tregeter, Morrison, and Seiberg, and many others. No? But these are geometric classification schemes. Particular in this context, you have analogs of orbifolds. You have the orbifolds of C3 modulo gamma, where gamma now is a discrete subgroup of SU3. So even more cases. No? And geometric classification scheme. Is there an atomic one? No? Would that make sense to find atoms for these theories? No? And that's the question that we answer in this work, no? Like, is there a 5D atomic classification? No, we don't go into the details of the classification. We don't even start. But what we start doing is we start trying to build 5D conformal matter, no? This is the first question. No? If you want an atomic classification, you need to have some analogs of 5D conformal matter. No? Is there evidence for 5D conformal matter? Well, some. No? If you look in the literature, there's this nice work by Waffa and Katz that says that if you collide AN-type singularities, no, you can construct bifundamentals at the intersection. No? So this is Katz-Waffa. Matter from geometry. And there is a nice work by Sergio, Francesco, and Tachikawa where they say, okay, but we can also do the 5D version of the trinions by taking PQ branes and smashing them together, and this will become a 5D version of a TN theory. Is the common intersection of collections of PQ webs, of PQ branes. These ones are dual to these orbifold singularities. There are some orbifold singularities that have precisely this structure and give rise to kind of 5D trinion theories of A type. To each leg of this PQ brane web there is an SUN. And so, yes, as in 4D, in 5D, there are fundamentals, bifundamentals, but also trinions, no? And there are examples of those. The question is, can we, exploiting geometry, identify the building blocks? Can we look for, like, building blocks of, like, I don't know, is there an E6 bifundamental in 5D that does not come from a 6D theory from a circle reduction, no? Like some intrinsic 5D conformal matter, different from the one that you would get from the circle reduction of the conformal matter in 6D. No? So is there 5D conformal matter without a 6D KK simple origin? No? Like, because of course there is, no, you take the 6D conformal matter, it has flavor symmetry G times G, you put it on a circle, you project down to the lowest KK mode, you get a theory in 5D that has that amount of flavor symmetry. But are there more? Or that's all there is, no? And in fact, the thing is, the outcome of the paper is that yes, there is a 5D conformal matter, and yes, there is 5D conformal matter that doesn't follow like so automatically from the 6D 1,0 one, no? And the recipe that we use to construct it is in fact very elementary, no? We just generalize this idea of Katz-Waffa to more general singularities, no? How is that realized? You are probably familiar with the Duval classification of singularities, no? They are, for instance, this would be the A type. No, this is an AN minus 1 singularity written like this, no? As a hypersurface of C3. This is the analog C2 mod Zn. And now what we want to do, we just want to do a base change. So we say that now Z is a product of two guys. And in this way, you see that now we have a thing, a threefold. It has we are using 4 coordinates. It's a hypersurface of C3 now. It's a hypersurface of C4, so it's a threefold. And when U is equal to 0, we have an AN minus 1 singularity here. When V is equal to 0, we have an AN minus 1 singularity here. When U and V are 0, the singularity enhances to A2N minus 1. No? This is how Katz-Waffa read out the matter from the adjoint decomposition, because they knew that in M theory on an A-type singularity you get an adjoint, and then you see like here you have an A2N plus 1. This would be SU2N, and the adjoint of SU2N, this splits into the adjoint of SUN plus the adjoint of SUN plus you have N bar plus N bar N plus 1, no? And so you see, these are the adjoint of the SUNs that are carried by these curves. And here the enhancement of the singularity says that there is a hypermultiplet in the bifundamental. These are the degrees of freedom of a hypermultiplet in the bifundamental plus a spectator singlet that you don't care about, no? And so, like, the idea now is, if you want to generalize this is how you construct bifundamentals. Well, why don't we take other singularities, no? Why cannot we take the E6 singularity? Like, it's x squared plus y cubed plus z to the fourth equal to 0, no? And we can do the same. We can say, okay, let's take y equal to uv now, no? What happens? We have again two curves of singularities, two curves of E6, no? U equal to 0 has an E6 singularity, v equal to 0 has an E6 singularity. They collide. They collide into something that is not that doesn't follow this conventional matter splitting, no? And so how can we study this? We use the geometric engineering dictionary between Calabi-Yau singularities and 5D CFTs. No? Just this one. I haven't done the classification for 6D. Well, yeah, I think so. Yes, like the bifundamental in 6D, the SUK bifundamental, the one that they know, is just a bifundamental field. It's not. You don't need anything more than that. No. For E6, E6, no. What is the point? No, if you try to do this in 6D, you would play a similar role, a similar game, but now you are looking at a different ambient space. No? You're doing F theory, and so you're writing elliptic singularities on an ambient space which is a P2 vibration over a Keller base. No? And the ambient space, the fact that you are writing it in a different ambient space is more constrained. No? So you have these Weierstrass models. No? And instead here we are just doing hypersurface singularities because we are intrinsically in M theory. So the ambient space is a C4 or some more general complete intersections, no? Such that they just don't have an elliptic uplift on the nose. No? The ones that have an elliptic uplift on the nose, so that you can fit in some Weierstrass model, they are the ones that come from 60. But there are more. Like this one that I wrote, I choose the base change precisely in such a way that I cannot embed it into a Weierstrass model. No? And that was the insight that Mario and Andrea had. Like let's try to all the possibilities, no? Because we tried, and the first one that we started from was the 6D conformal matter theory, and there you get the quiver that we were expecting. But here you start with one that doesn't, and so you expect to get something more, and we do. And you can understand these systems exploiting these dictionaries between Calabi-Yau threefold singularities, say X, and 5D CFTs, say T of X, no? And from these dictionaries we can try to read off what are the resulting theories from studying their Coulomb analog of Coulomb branches. They are geometrized by the moduli space of these singularities. No? So how does it work? There is a singularity, and then there are the resolutions of the Calabi-Yau, no? Something like this, and then they split. You have pictures like this. No? Each of these wedges correspond to a resolution of your singularity. Something like this. Here is where the CFT is located. Here is probably where the Higgs branch of the CFT will emanate. And then there are Higgs branches all over the place, no? But they are mixed. And there is the tensor branch. The tensor branch is split into chambers. Like crossing these internal wedges gives you a flop transition. And flop transitions are associated to the fact that from your threefold geometry you can get an effective action. The effective action breaks down here because there are some BPS particles that become massless, and you have to change the superpotential. The triple intersection number of your geometry changes, you get a birational equivalent one. But there are outer edges here. The outer edges are where strings become tensionless. So the M5 brane that wraps a divisor becomes tensionless. There is a full divisor that shrinks. That's a hard wall. You cannot cross it. No? And like naively looking at the constraints arising from the positivity of the metric that you could compute from the potential, people ruled out 5D quiver gauge theories. They say, no, like the metric will become negative definite. For a quiver gauge theory, it cannot exist. But that's because they look at points that were outside. No? So if you look at the point here, your effective action breaks down. You cannot use it to describe it. You have to keep track of the fact that there are these rigid walls. And so the naive Coulomb branch is smaller. There are some hard walls where the tension of your strings becomes zero. And this was realized like, I don't know, 4 years ago, more or less, in the literature. It was Waff and collaborators that explained this. And now the idea is that keeping into track the fact that there are these hard walls, then this enlarges the space of CFTs. So there are 5D quiver theories that have conformal fixed points. And of course, this is 5D theory, so RG flow is a bit weird, no? Like it's nonsensical to speak about gauge groups in 5 dimensions because the gauge coupling is a relevant deformation, so it will just flow to an infrared free theory. But the idea is that you start from a 5D fixed point, you give a relevant deformation, and that relevant deformation gives you a gauge theory phase, which is like some point inside here in your Coulomb branch. No? Now, so with this type of dictionary, we can look at what happens if we collide these, and we go in a special chamber that we can try to understand. No? So what happens if you do this? Yes, it's a mass. Yes, it's a mass for the U1 topological. No, the gauge coupling of in 5D. And what do you do? Let's do it. No, for this example, you start blowing up you start blowing up these singularities, and here is where Michele Graffeo help was really needed, because these are pretty messy objects to blow up and to understand the geometry of. And if you do that for this geometry, the result is pretty scary at first, but it is simple enough that we can draw it on the board with some extra words to explain it. So you see, each of these hexagons is a blow up of a Hirzebruch surface in 2 points. And so each of these curves, from the perspective of the Hirzebruch surfaces, are -1 curves. All of these, no, -1, -1, -1, -1, all the ones. And this says that this collection of surfaces has a vibration in the direction transverse to the blackboard, in which this zero curve becomes a -2 because of the Calabi-Yau condition. And so there is maybe I can borrow one of your colored chalks. Is it okay? So let's do it in red. So here there is a -2 curve. Here there are 2. Here there are 3. 2. 1. And then, and this is where the help of Graffeo was really useful, there is another surface, another color, maybe let's do yellow, which kind of comes comes outside of the board, say, something like this. Okay. So this one has another -2 curve. Can you see it? There is like a surface coming, the yellow surface is coming out of the board, no? It has another vibration by a -2 curve, and it meets here along an A5 singularity. Okay. So from this geometry, we can read off a quiver, because to every -2 curve, we can associate an SU group. If we shrink it, we get an A1 singularity. We shrink this one, we get an A2 singularity. This one behind an A3. And so we see that there is an SU2, an SU3, an SU4, an SU3, an SU2, and then the yellow one becomes an SU2. And then since here there are these little enhancements, there is some flavors. So here there is a 1, and here there is a 1. Oops, apologies, yes. Apologies. Yes, this is the resolution of that. Each of these faces is a surface, is a divisor, no? And here I'm indicating the self-intersection of the various curves, no? And it's hard to do it. Like you have to perform blow-ups and blow-ups and blow-ups. And yeah. That one is the yellow one, yes. And the fact that it meets along an A5 singularity is this bifundamental according to the Katz-Baffa dictionary. No? Each of these are bifundamental. So the idea, what is the message? The message is, this thing, we claim it has an E6 global symmetry. Can we check it somehow, studying the Coulomb phase description? along the Coulomb phase, we find a gauge theory phase, a gauge theory description, in terms of these gauge groups. This is a deformation, no? It's a place here. Does this enhance to E6 times E6? Well, there is a nice criterion by Tachikawa and Yonekura. They say if you have a quiver that has the shape of a Dinkin G type diagram with a matrix like this, ranks that satisfy this constraint, and flavor symmetry that satisfy this other constraint, then the flavor symmetry in the UV of this theory contains G times G. And so this diagram here, you see, it's a quiver that has an E6 shape. The ranks, you plug them in, and the flavor symmetry, you plug them in this formula, they satisfy the Tachikawa-Yonekura criterion. And so the resulting theory definitely has an enhancement to E6 times E6 as a flavor symmetry. So this was a consistency check for our claim.
Can I think of this as sort of magnetic quiver?
No, this is the electric quiver. It will have a magnetic quiver from which you can compute its Higgs branch. This is the electric quiver, yes. It's an electric quiver for the tensor branch, for a point on the tensor branch. Okay? Coulomb branch, yes, Coulomb branch. So,
If I forget this electric and I think that some 3D gadget, can I don't know, calculate?
Yeah, I think so. Yes, definitely. Yes. I think that Amihai, looking at this, told me that it was some minimal nilpotent, some next to minimal. He recognizes these numbers. I don't know how he does. And yeah. You can probably extract interesting information about these CFTs from the magnetic quivers of these. No, they capture the Higgs branches. So it would be interesting to study. I think it's interesting. So this is okay. Yes, exactly. So I think that if you start from here, you get the magnetic quiver at finite coupling, and then there will be some trickery that you know how like better than me. But from geometry, what we read off is just this, and we just use it as a consistency check of the claim that this theory has F times F flavor symmetry. But I don't know. There is another question, which is, okay, this now shows that this is a CFT with the 6 times C6 flavor symmetry. Does it quiver? Can I start gauging these E6s and build the linear quivers? And the answer also here is surprisingly simple in geometry, because you can just change the base change. You add an n here. You get these E6s that now meet at an A-type an minus 1 singularity, and then you get quivers with n copies of that have exactly the structure that I wanted. So they have E6 gauge symmetries, no? E6 gauge, E6 gauge, and you can build a linear quiver as long as you want, no? With the final flavor. You can just use them. They are Lego pieces. You can write an infinite series of theories with flavor symmetry 6 times C6, C7 times C7, E8 times C8 with this trick. And there is one for each coordinate. So there are, in fact, three series of these theories. And in each case, we can do the resolution, and we can see that the flavor symmetry enhances. If you choose, for instance, this one, the quiver gets modified just by multiplying every factor by n. So you get an n here, 2n here, 3n here, 4n here, 3n, 2n, n, and 2n when this is n, no? And so it's very like functorial in a sense, no? And they satisfy again this constraint because just rescaling by a linear factor, no?
Why
yes.
do you call this theory an atom? Because you can itself is a quiver. You can think of it as fundamental tomorrow.
That's a good point, no? But the point is that, like, why do we call them atoms? Because we can use them to build E6 quivers, no? Which you wouldn't say if you just look at this. You wouldn't say that you are building an E6 quiver, and like it's a quiver tail. So I don't know whether you can do something more. I don't know whether you can loop it. I like there are like the point of the project is not to do the atomic classification, is to show that if one wants, one of the building blocks, the bifundamental conformal matter, is there. No, that's the purpose of the paper. No, and yes, exactly. There will be probably more dualities and like all stuff that has been done from geometry can be done to understand better the properties of 5D conformal matter theories. They occur in families, so it's nice. They might even have a large n limit. I don't know. Like it's up for grabs. And what else can I say? Oh yes, like it's interesting to remark that if you start from the description of the A-type singularity, no, there is another form of the singularity, which is this one. No, and if you do the base change, like the one that I suggested was just take z equal to uv, but you can do it for y. You will get a singularity which is x uv equal to zn, and this one is the Calabi-Yau geometry that correspond to the orbifold C3 mod zn times zn. And so you get the trinion, the 5D trinion from the base change trick is part of this family. So the question is whether there are other collisions, maybe other trinions. We looked into it, we found some candidate geometries for GG prime bifundamentals and one D-type trinion. And there is a question, an open question, which is there is a criterion by Tian and Yau about when certain singularities are at finite distance in Calabi-Yau moduli space. That criterion applies for isolated singularities. Here, the singularities are not isolated; they occur in. And so the question is, like, if you commit to that criterion, then it seems that certain trinions are ruled out. But maybe that criterion can be weakened in the case of non-isolated singularities. And if that is the case, then we could also find geometries that give rise to the trinions, but they will appear in a follow-up once we understand better the mathematics of the Tian-Yau criterion for finite distance in moduli space. And so, yes, the punchline of the talk is, well, there is 5D conformal matter. And so maybe there is an atomic classification scheme for 5D CFTs, and definitely there is a different perspective on 5-dimensional theories that we might have known from this structure. So, for instance, this statement is a statement of a duality between a quiver of this type with n components, an E6 linear quiver, and this gauge theory. No? So this is another 5D duality, if you wish. And there are many more, as Cyril suggested. Now, if you look at the structure of the generalized Keller cone of these Calabi-Yau geometries, you might find more gauge theory interpretation, more structures, and like, well, yes, this is it more or less. Yes.
What is your gauge? So here you have an example of the atom which have GAG.
Yes.
So here by the gauging you determine.
Yeah, I literally mean that if you study this geometry, you will find out that there are copies of these theories, no, where there is a compact curve supporting an E6, which is shared by two of these elementary building blocks. So you can literally, like from geometry, you can literally see that if you do that base change, you find a pattern like this, where each edge is one of the elementary conformal matter, and they are gauged in 5D now by adding E6 gauge groups. So it's literally you find the E6 gauge degrees of freedom from the M-theory engineering, and as many as the nodes that you need, and with like it's just a local patch, no, in the geometry. You resolve the Y-type singularity, and then at each of the collisions in the resolution, you find that there is a copy of this one. No, so that's how we see it. Sorry.
What does that make you're doing the single base?
Yes. Yes, exactly. That's what I said. No, I said that there are for every choice of Duval singularity, there are 3 5D conformal matter theories arising from this base change trick. One of them will be the 6D one, the one that you obtain from circular reduction of the 6D theory. The other two, they are new, yes. And like this one, you see, it clearly has a 5D origin because the 6D one would have a structure here that is like that of an affine quiver, with the nodes that are in the minimal affine minimal imaginary root of E6, and here it's different, no? Because that one would have a 1, 2, 3, 3, 2, 1, 3, 2, 1. So they have a different structure. Yes. Will change, yes. No? The criterion here, the criterion that I erased, the criterion by Tachikawa and Yonekura, was a criterion that they established because when we found the conformal matter in 6 dimensions, we knew that they had a dual which was a Douglas-Moore type of quiver with the assignment given by the minimal imaginary root. And they were saying, but now we proved that they don't have an enhancement to GG type, no, to a flavor symmetry which enhances to E6 times E6, no? And instead, no, they found that it works. And the criterion is even more general, so we can use it now to prove that even these examples work, no? So it's a nice application of their result, I think.
In principle, you should have a similar result for the top quiver, where the U1 to the 2n and
Which one?
So in the bottom quiver, the Tachikawa Yonekura,
Yes.
just a normal Lagrange.
Yes.
But then if you look at the top quiver,
Yes.
it's 6 times 6, but then there is also the SUN times SUN.
And
It comes from the enhancement of the topological plus axial of the generalized.
You say for this quiver? No, this quiver has a symmetry E6 times E6. The global symmetry of this one.
The bottom one, which is SUN times SUN on top of the 6 times.
No, this one has E6 times E6.
But also SUN times SUN. Because you have two global SUN.
I see what you mean. Yes, this is a nice remark. Yes.
Should be a similar
There should be a similar story there. Yes, I agree. Yes. It works, indeed. Yes.
You know, geometrically, there is something to start with. Here you have threefold with some ideal singularity phi, which is canonical threefold with some canonical twofold. So you can define. You can have intersection of 2, you can intersection of 3 is like the Trinian. What stuff you are having intersection of many more?
Yeah, that's the question is whether those can be obtained factoring out, like in the class S story. You know, you have a sphere with 4 punctures. You can always, there is always some unexactly marginal deformation that takes you to a sphere with 2 spheres with 3 punctures and a gauging. Here, I don't know whether there is an analog operation. For the toric threefolds, of course, no, because the toric threefolds like this orbifold, they would have you can start playing the same game that you have in class S, no? You know, this would be the one for a sphere with 4 punctures, no? But there is a clear cut, no? And you can kind of make this divisor non-compact, and yeah. So it's I find it interesting as a question. I don't claim I have an answer. But at least I have evidence that 5D conformal matter by fundamental type exists. So that's a starting point, if you wish, but definitely not conclusive. I mean, I think that there are many questions that are open and are interesting to.
You just like to reduce it that way, like here you might have like on UX, on UV or whatever, you can reduce it that way.
Yes, exactly. Yes, from our story, yes, we can definitely get this from there. But the issue is that here, you see, this is non-toric, no, because there is this. But definitely, yes. But we haven't looked into that. We just read the quiver from the resolution. We haven't tried to dualize to type 2A. So it might be interesting to try to see whether this gives rise to more general configuration. With Cyril, we wrote a paper a few years ago where we discussed gauge theory spaces from reductions from M theory to type 2A. And there, like, the quiver gauge theory arises from wrapped D6 branes. And now, like, in the examples that we checked, the quivers were always linear, which corresponds to the fact that the Calabi-Yaus were toric. But this seems to suggest that this works also for Calabi-Yaus that are non-toric, and that can give rise to more general compactification geometries in type 2A. It might be interesting to investigate further, yes. Okay.
Thank you, Michele.
Thank you.